Okay, so I'm going to walk through these examples of free body diagrams, and we'll go from the easiest one to number 1 and work our way up. Alright, so there's 4 forces that we can have. We can have weight, gravity, we can have friction, we can have normal force, and we can have tension. So in each case, we're just going to draw an arrow for each one of those 4 if it's present. So the first example, we've got a box sitting on a surface, and we say that the box is stationary. So what forces do we have present? We always have gravity, and gravity is always straight down. So I can draw my vector there for gravity. Do I have tension? No, there's nothing about a rope, so there's no tension. Do I have a normal force? Yes, it's sitting on a surface. Whenever it sits on a surface, there's a normal force. So I draw my normal force upwards. And the box is stationary. So if the box is stationary, then the acceleration is 0. So that means that the total force is also equal to 0. So what do I have for my total force? I've got normal force up, gravitational force down. They have to be the same length arrows because they're equal to each other. So I write the sum of the forces is Fn minus Fg, and that's equal to 0. Draw my axes. Well, in this case, I have y up and x across. Okay, so that one was pretty simple. Next, let's move on to situation 2. Now, situation 2, we've got the box sliding to the left at a constant speed on the frictionless surface. So let me draw my axes. So I'm going to choose standard axes, x across, y up, because I've got a nice horizontal situation. What forces do I have? Well, just like before, I've got gravitational force down, normal force up. All right, what about the other 2 forces? The other 2 forces were friction. Do I have friction? No, it says it's frictionless surface, so no friction. What about tension? No, I'm not told that I have any tension, so I don't have any horizontal forces at all. This is exactly the same as situation 1. What's the acceleration? Well, the acceleration perpendicular to the plane is 0, just like in the previous case. Why is it 0? Well, almost every situation we have where something's sitting on a surface, it's not going to levitate up off the surface, it's not going to fall through the surface, so the total force perpendicular to the surface, so in this case it's the y direction, is 0. How about in the x direction? Well, there's no acceleration. It says constant speed. Constant speed means acceleration equals 0. So that means that the total force in the x direction is 0, and there's no forces in the x direction anyway, so the total force in the x direction is 0. So situation 1, where the object is stationary, and situation 2, where it's moving at a constant speed, are exactly the same as each other. There's no acceleration when the object's stationary, there's no acceleration when it's moving at constant speed, so we have exactly the same setup. Okay, situation 3, we're going to kick it up a notch. We're going to make it go on a rough surface, so we're going to have friction in this case. Alright, so what do we have? Well, same as before, we've got gravity down, normal force up. Normal force is always perpendicular to the surface. How about friction and tension? There's no tension. We're not told about it being pulled in any direction, but there is friction. What direction is friction? Friction is always parallel to the surface in the opposite direction to the direction the object's moving. So the object is moving to the left, so friction will be to the right. Okay, so those are my only 3 forces. What do I have for acceleration? Well, again, it doesn't leap up off the surface, it doesn't fall down through the surface, so there's no vertical acceleration. What direction is the horizontal acceleration in? Well, the object is moving to the left and slowing down, so that means the acceleration is to the right. So my acceleration is in that direction. Alright, so what axes do I use? It's a horizontal situation, so I'd use x being horizontal, y being vertical. And again, sum of the forces perpendicular to the plane in the y direction add up to 0 because it doesn't levitate up off the surface, it doesn't fall down through the surface. So normal force minus gravity equals 0. How about in the x direction? Now in the x direction, I do have an acceleration, so the sum of the forces in the x direction is going to add up to mass times acceleration. And what forces do I have in the x direction? The only force I have is the force of friction. Okay, so we're done this one. If we were given masses and coefficients of friction, we'd be able to find the acceleration, and we'll work on that a bit later. Alright, next one. Now I've got an object on a rough surface again, but now it's being pulled by a rope towards the right. The rope, you can see, is tilted slightly upwards, and it's speeding up. Alright, so what do? Draw my free body diagram, and this time I'm going to start on this side since my force is going the other way. What do I have? Same old, same old. I got gravity down, normal force up. Friction is parallel to the surface in the opposite direction to what it's moving, so it's moving to the right, so my friction is going to be to the left. Alright, what about the tension? Tension is up at an angle theta, so I'm just going to reproduce that here. And again, remember, when you're drawing a free body diagram, just draw your object as a dot. You don't need to draw on the surface, you don't need to draw the box or the shape of whatever it is that's moving. So this is my force of tension. Alright, so what do I know? I know the thing is accelerating towards the right. So that means that if I draw my axes in, again, it's a horizontal surface, so I'm going to do x is horizontal, y is vertical. So the sum of the forces in the y direction is going to be 0. Sum of the forces in the x direction is going to be m times a. Those are just Newton's second law. Alright, so what forces do I have in the y direction? Well, I've got my normal force, I've got my gravitational force, just like I had in examples 1 through 3, but now I've also got a component of the tension. If I look at my triangle for the tension, let me draw it here below. I've got my tension going like this. That angle's theta. I've got Fty. The y component of the tension is going up, and I've got the x component of the tension is going across. I can figure out what these components are by looking at my triangle. Just do trig like we did in chapter 4. This side is opposite to the angle, so that's going to be sine theta. This side is adjacent to the angle, so it's going to be cosine theta. So in my y direction, I've got normal force up, I've got Fty up, and I've got gravity down. And remember, gravity is always equal to m times g. So again, if we know the m, we can get the force. Sum of the forces in the x direction, that has to add up to ma. Well, in the x direction, I've got the horizontal component of the tension forward and friction backward. So I've got Ftx minus force of friction is going to be equal to ma. Remember, the forces in the y direction add up to 0. Okay, remember too, the force of friction is equal to mu times the normal force. So again, we can work through, if we're given a few numbers about friction and mass, we can work through and find what all of our forces are. Okay, example 5. Now what we've done is we've moved to a situation where we've got something moving on an incline. Right, so on an incline, what do? What we do is we make our x-axis parallel and our y-axis perpendicular to the ramp. Okay, so what forces do we have? Well, we've always got gravity. And what direction is gravity? Gravity is always straight down. So I'm going to draw my gravity straight downwards. I've got my normal force. Whenever anything is sitting on a surface, I have a normal force. What direction is the normal force? It's perpendicular to the surface. So it's going to be perpendicular to the surface of the ramp. So it's going to be up at an angle like this. Alright, what do I have else? The other two forces are friction and tension. Do I have a rope? No, no rope, so no tension. Do I have friction? No, the question says it's frictionless ramp, so there's no friction. So I only have those two forces. What direction is the acceleration? Well, it's down the ramp, so the acceleration is down the ramp like that. Alright, so now what do I know? Well, sum of the forces in the x direction has to add up to m times a. Remember, I've twisted my x direction around so it's going down the ramp in the direction that the object's accelerating. So what forces do I have in the x direction? Well, if I draw my axes onto this picture, My y direction is perpendicular to the ramp, just like the normal force. My x direction is parallel to the ramp, so in the same direction as A. So my normal force is all along the y direction. So the only force that can be going along the x direction is gravity. So if I've got my ramp at an angle theta like this, and gravity acts straight down, so I'm going to draw it in the top picture here, gravity acts straight down, this angle in here is theta. Okay, it's good geometry practice for you to go through and try and prove that, but take it from me, it's equal to theta. If you don't believe me, come and talk to me sometime and we can work it through. Alright, so I know that this angle in here is theta. So now what I want to do is I want to find how much of my gravitational force is along the y direction, which is this component, how much of my gravitational force is along the x direction, which is this side of the triangle. So I want forces in the x direction first, so let's start with that. Force in the x direction, it's only this side of the gravity in the x direction, and that's going to be equal to, since it's opposite to the angle, it's going to be mg sine theta. Okay, so I've got fgx is equal to mg sine theta, and that's equal to the mass times acceleration. Okay, how about in the y direction? Well, what do we know about some of the forces in the y direction? Y direction is perpendicular to the ramp. We know the box doesn't levitate up off the ramp. It doesn't fall down through the ramp. So that's got to add up to 0. What forces do I have in the y direction? Well, I've got my normal force is straight in the y direction. So I've got my normal force up. And what else do I have? I've got to have something else, because remember, I can't get 0 just by adding one thing. I'm going to have to subtract something that's equal size from it in order to get 0. So what do I have? I've got the y component of the gravitational force. So that's this side of the triangle, which is adjacent to the angle. So minus fgy. So I've got fn minus mg cosine theta is equal to 0. Okay, so you can see now, if I knew my m and I knew my theta, I could get my normal force. And if I knew my m and I knew my theta, I could get my acceleration. So again, if you're given a couple of numbers, you can get every force in the problem. Alright, so now let's just add in friction. So now we've got the same situation, but the object's going down a ramp with friction, and it's speeding up going down the ramp. So what we've got is exactly the same thing as we had in 5, except we've got friction added on. So we've got normal force perpendicular to the ramp. We've got gravity straight down. We've got friction now, and friction is in the opposite direction to what it's moving, and it's parallel to the surface. So it's going to be backwards up the ramp like this. And again, since it's on a ramp, we're going to choose our axes so that x is going down the ramp and y is going perpendicular to the ramp. Alright, so sum of the forces in the x direction is equal to the mass times the acceleration. Since the acceleration is down the ramp. What forces do I have in the x direction? Well, as before, I'm going to have the x component of the gravity. So that's this side of the triangle, and it's worked out exactly the same way. So it's going to be mg sine theta, so fgx. And I also have frictional force acting backwards, and remember my x-axis is along here parallel to the ramp, so the frictional force is just all in the minus x direction. So it's minus the force of friction is equal to 0. So I can see then my force of friction is equal to the mass times the acceleration. In the y direction, again, what's it add up to? 0, because it doesn't levitate up off the ramp, it doesn't fall down through the ramp. What forces do I have in the y direction? Well, it's exactly the same thing as what I had before. It's normal force minus the y component of gravity, so normal force minus mg cos theta is equal to 0. So if I'm given my mass and theta, I can figure out the normal force. And remember, if I know my normal force, the force of friction is just equal to mu times the normal force. So then I can get a number for my normal force and work backwards. And again, we're going to work on that a little bit later. Okay, let's move on to the second page. Alright, example 7. Now I'm sliding up a rough ramp. Again, rough means friction, and slowing down. So now this is just the opposite of problem 6 in terms of direction. Alright, so now what do we do that's different? Normal force is still going to be perpendicular to the ramp. Gravity is still going to be down. The only thing that changes here is the direction of our friction force. Remember, friction is opposite to the direction of motion. So in problem 6, when we were sliding down, then the friction was up the ramp. Now I'm sliding up, so the friction is down the ramp. So there's my force of friction. Again, my axes are going to be with my y perpendicular and my x parallel. What direction is the acceleration? Well, it's going upwards and it's slowing down. So if it's slowing down, then the acceleration is in the opposite direction to motion. So the acceleration is in the x direction. Alright, so again, do our equations. Sum of the forces in the x direction equals mass times acceleration. What forces do I have in the x direction? I've got the force of friction is going down the ramp, and I've also got, as we had before, the x component of gravity, which is going to be mg sine theta because it's opposite. So I've got force of friction going down the ramp. I've got the x component of gravity going down the ramp, and those have to add up together to be mass times acceleration. So you see the difference between number 6, if you go back, is that rather than subtracting the friction from the x component of gravity, we're adding it because they're now going in the same direction. Alright, in the y direction, what do we have? Well, they got to add up to 0. Again, it doesn't leap up off the ramp, it doesn't fall down through the ramp. We've got normal force up minus the y component of gravity down, so that's minus mg cosine theta down is equal to 0. So again, we can find the normal force if we know m and theta, and then using the normal force we can find the frictional force is mu times the normal force. Alright, number 8. Now I've got my block sitting on a ramp, but now the friction is so high that the block isn't moving. So what do I have that's different? If it's not moving, acceleration is 0. So same situation as before. Normal force is perpendicular to the ramp. So my ramp is pointing in this direction. So my normal force is perpendicular to the ramp. Gravity always goes straight down towards the earth. Alright, what else do I have? I've got a frictional force. What direction is friction? Well, static frictional force is in the direction opposite to the direction the object would move if it were to slide. It's in the direction that's preventing sliding. So the block wants to slide down, so the frictional force is up the ramp. Okay, so now, again, I want to do total forces. Sum of the force in the x direction is equal to the mass times the acceleration, and the acceleration, since it's not moving, is 0. Total force in the y direction, again, always on a surface, it doesn't leap up off the surface, it doesn't fall down through the surface. So I've got total force in the y direction is 0. If I look at my forces, what do I have in the x direction? In the x direction, so again, remember my x-axis is going along the ramp, y-axis perpendicular. Force of friction is straight up the ramp, so I've got force of friction up the ramp. Downwards, I've got the x component of the gravitational force, which is this side of the triangle here. So it's going to be mg sine theta. And you notice I put a minus sign because it's going down in the opposite direction to the x direction. And that's equal to 0. So that means the force of friction is just equal to mg sine theta. Sum of the forces in the y direction equals 0. So the forces in the y direction equals 0. I've got my normal force all in the y direction minus the y component of gravity, which is this side of the triangle. That side's adjacent to the angle, so it's cosine is equal to 0. So you should be seeing now that there's this pattern that's emerging that's always the same. Okay, let's do another ramp one. Now I've got tension in here. I'm pulling an object with a string. You see the string is parallel to the ramp surface, and it's increasing in speed up the ramp. So that means my acceleration is up the ramp. Okay, so what forces do I have? Well, same old, same old. Normal force perpendicular to the ramp, gravity straight down. What else do I have? It's a rough ramp, so I've got friction. What direction is the friction? Parallel to the ramp in the opposite direction to the motion. So that's going to be down here to the left. What else do I have? I've got tension. The tension is going straight up the ramp. So there's my situation there. Okay, so now some of the forces. Some of the forces in the x direction, that's up the ramp. So let's draw our axes on, x and y. Some of the forces in the x direction adds up to m times a. Some of the forces in the y direction has to add up to what? Well, again, that's perpendicular to the ramp. It doesn't leap up off the ramp. It doesn't fall down through the ramp. I bet you're getting tired of hearing me say that by now. So that adds up to 0. Alright, so what do we have in the x direction? X direction, I've got tension straight up the ramp, friction straight down the ramp, and is there anything else? Yeah, remember gravity. So there's my angle theta. I've got x component of gravity, which tends to pull it back down the ramp. It's working against the tension. So in the x direction, I've got force of tension up, minus the force of friction down, minus the x component of the gravity, which is mg sine theta. That adds up to ma. In the y direction, I've got normal force straight in the y direction, and I've got the y component of gravity, which is this side of the triangle, minus mg cosine theta downwards, and that adds up to 0. Okay, now let's look at something a little bit different. Now I've got an object that's just hanging from the ceiling. Alright, so what forces do we have that are present? So let me draw a free body diagram, start with a dot for the object. Well, we always have gravity, and gravity is always straight down. What else do we have? Well, we're going to have tension, right, because it's hanging from a string, and tension is always parallel to the string. Do we have any horizontal forces? No, there's no normal force because it's not sitting on a surface, and there's no frictional force because there's no surface. So we've got tension up, gravity down. What's the acceleration? Well, it's just hanging there, so there's no acceleration. So that means that my tension force upwards has to be the same as my gravitational force downwards. So Ft minus Fg equals 0. Okay, let's do the same situation, but now we're going to tilt it. We're going to put it on a ramp. We're going to have a block tied to a wall at the top of a ramp. And we're told that the ramp is rough, so that tells us there's going to be a frictional force. Alright, so now what's the situation? Well, it's going to be the same as anything else on a ramp. We're going to have normal force perpendicular to the ramp, gravity straight down towards the ground. We've got a frictional force. What direction is the friction? Well, the friction is going to be such that it prevents the object from sliding. So the object would normally slide down, so the frictional force must be up the ramp. And we've also got a rope, so we've got a force of tension up the ramp. Okay. What's the acceleration? Acceleration, object is stationary, acceleration is 0. So that means the total force in the x direction is going to have to add up to 0. Total force in the y direction is going to have to add up to 0. Alright, so let's draw our axes. I can draw them any way I want. Let me put x going down the ramp and y going perpendicular. So sum of the forces in the x direction is 0. What forces do I have in the x direction? I've got tension going the minus x direction, so minus the force of tension. I've got friction going in the minus x direction, minus the force of friction. What else do I have? I've got the x component of gravity going down. Remember, since both of these two forces are going up the ramp, if they're going to add up to 0, I've got to have another force going down the ramp. And that's going to be the x component of gravity. So again, this is theta. Where opposite x component is mg sine theta. In the y direction, what do I have? I've got normal force straight along the y-axis, so Fn up, and then I've got the y component of gravity minus mg cosine theta going down. You'll notice in all these examples that the downwards component of the gravitational force is always mg cosine theta, and the component along the ramp is always mg sine theta. Okay, last example, now we've got two objects. So I've got a frictionless surface. I tie the two blocks together. What's going to happen? Well, what's going to happen is that block B is going to slide down and block A is going to slide across. And they're going to have the same acceleration as each other because they're tied together with the same piece of string. So that means they're going to have to move as fast as each other, and they're going to have to accelerate at the same rate, or the string is going to snap. Alright, so what's going to happen here? Well, I have to draw two free body diagrams. So I have to draw one for A and one for B. So let me divide my area into two here. Draw one for A. What do I have for A? Well, on A, I've got normal force up, it's sitting on a surface. I've got gravity down. And let's call it FGA because there's going to be gravity on both of them. And I've got the tension in the string. There's no friction in this case, so I don't have to draw any more arrows. Alright, sum of the forces in the y direction is 0. It doesn't leap up off the surface, it doesn't go through the surface. So I know that that's the normal force minus the gravitational force of A, which is just going to be the mass of A times G. In the x direction, sum of the forces is MA, and that's just going to be whatever the tension is in the rope. Okay, how about object B? Well, object B is not sitting on a surface. It's not sitting on a surface, so that means it's just like in example 1. It doesn't have any normal force. All it's got is the tension pulling it upwards, and it's got the weight pulling it downwards. There's no horizontal forces at all. So we know the sum of the forces in the y direction has got to be equal to the mass times the acceleration. And now I have to be a little bit careful because the acceleration is downwards. Okay, so I can either put in a minus sign here to indicate that the acceleration is downwards, or I can work it in later. But let me put it in there. So then I have that the force of tension up minus the force of gravity on block B down is equal to minus mass of block B times A. And in fact, over here I should have made sure I put in mass of block A in this equation. And so again, if you're given the masses of the two objects, we should be able to find out the acceleration. So these are just 12 examples, and you'll see that it comes out down to maybe 3 or 4 different cases. We can have things that are hanging, we can have things on ramps, or we can have things on horizontal surfaces, and there's just a few steps that you have to do to make a successful free body diagram and set of equations for each one. And once you've got the set of equations, then you're well on your way to solving the problem.